Assalamualaikum. Good afternoon. Can you hear me?
Yes, doctor.
Yes, doctor.
Okay, so Bismillahirrahmanirrahim. Today we are going to move to chapter 2. So since chapter 2 is the total slides is about 150. So I divided into two sections, chapter 2A and chapter 2B. So here I give you chapter 2A, which is on the PID controller design. So my lecture will be based on the listed subtopic, which is introduction by revisit to the time domain analysis, design with gain adjustment, and then improving the steady state error using proportional integral controller or PI controller, then improving the transient response from slow become faster by using a proportional derivative controller, then improving transient response and steady state error simultaneously, which is using a proportional integral and derivative controller, PID. And then second last topic will be the Ziegler-Nichols tuning of PID controller. And then controller design using MATLAB will be applied during the lecture, okay, by sharing the MATLAB software. So as you know that root locus is a powerful tool design in the control system. So using these tools, root locus, we will design gain adjustment or P controller, okay? Another name for gain adjustment is P controller, PI controller, PD controller, and PID controller. So for PID controller, we have to add another subtopic, which is for the tuning, okay, of the PID controller, because we need to tune the three values, which is the KP, KI, and KD, in order to achieve the best and optimal value for the Ziegler-Nichols tuning PID. So in control system, several inputs are used and injected to the system so that we want to see the response of the particular output. Okay, so the first one is the impulse response. Okay, the second one is the step response. Third one is the ramp. Number 4 is parabola, and number 5 is sinusoidal. And the descriptions, function and description are shown here. And the graphic or sketch of the impulse is a straight line at t equal to 0. Then a step, okay, is a square wave. And then a ramp usually is a triangular wave. Parabola is the exponent, and sinusoidal, which is shown as a sine wave. Okay, so each of these input have their suitable applications as shown on the right hand side. For example, for impulse, we usually use it for transient response and modeling. Okay, for step, we usually use for transient response and steady state error. Okay, steady state error is the difference between the input and output. And then for ramp, you usually apply to the steady state error, similarly to parabola. And for the sinusoidal, we are usually used for frequency domain response, okay, modeling and steady state error as well. So by this stage, I hope that you already know what is the definition of the poles, okay? which is the roots of the denominator transfer function, and the definition of zeros, which is the roots of the numerator. So poles and zeros between open loop and closed loop have a different value, okay, as we learned in the root locus theory. So poles and zero can be mapped using S-plane, okay. It's a linear graph, okay. So poles is usually labeled as X or cross, and zero as O, okay. So this is important in control system analysis. So first order system that we learned in the last semester in the previous control one has a response as shown here, okay, as shown in the blue line. And from this first order time response, we can obtain on the specific information, which is the time constant, the rise time, and the settling time. So usually, time constant is the important parameter, which is 63% of the final value. Okay, so if the final value is 1.0 over here, so the 63% is 0.63, which is 63% multiplied by 1. Okay. And then rise time is T 90% multiplied by T 10%. So this is the location of the T 90%. And this is the location of the T 10%. So rise time usually is T 90% multiply T 10%. Okay. And finally, the settling time is shown here, which is here, okay, at this point, which is a settling time. So usually we call it as 4 divided by A. A is the 1 over time constant. Okay. Okay, guys, clear? Hello? Okay? Hello?
Okay, Doctor.
Okay.
Okay, Doctor. Okay,
Don't
Doctor.
sleep, don't sleep, it's 12 o'clock. So second order system is also we studied in the last semester, which is represented by this transfer function. Omega n is the undamped natural frequency. Zeta is the damping ratio. Okay, also omega d is not listed here, but it is omega n 1 minus zeta square. So the second order response are determined by the damping ratio zeta and the undamped natural frequency omega n. So omega n and omega d is both are natural frequency. One is undamped and the other one is damped. So it can be categorized into overdamped, underdamped, undamped, critical damped, and negative damped based on the damping ratio and pole locations. So if we look at the general second order system shown here, where B and AB is the coefficients, okay? So for overdamped, okay, this is a sample for overdamped. So the roots are real and different, okay? Real roots, okay? And different value. So it's located on the real axis sigma, okay? And this is the type of response for overdamped. Okay, so usually overdamped is greater than 1. And then we go for the underdamped. Okay, so underdamped is the second type of second order system. And the type of roots is complex conjugate poles. Okay, complex conjugate. CC is complex conjugate. Okay, for this example is square root 8. And the type of the graphic response is it goes up, some overshoot, and goes down and settle at 1. And then for this underdamped, usually the zeta is between 0 and 1. The third type is the undamped. Okay, so undamped is zeta is equal to 0, the damping ratio, and the pole locations imaginary poles. Okay, so no real. So the poles is located on the top of the imaginary axis. Okay, and the response is quite different from the previous two response. So it is oscillate. Okay, oscillate when t towards infinity. So it is oscillate. Okay, which is not good for the system. And then critically damped is when the zeta is equal to 1 and the roots are the same roots. Okay, but overlap each other. Okay, overlap each other. So you can see that the -3 is overlap between each other. That's why the sign is like this. Okay, like H. And the time response is shown here. So the one that I just discussed now is undamped, underdamped, critical damped, and overdamped. Okay, so there's another one which is known as zeta is less than 0, which is negative damped. Okay, it's not listed in the book because negative damped always relate to the unstable system, and the response is okay, oscillate and becoming bigger when times towards infinity. So this is the 4-in-1 graph to show that the behavior and the difference between undamped, underdamped, critical damped, and overdamped. So for control system, the best zeta is between 0 and 1. Okay, the best one is 0.707 in order to design control system or mechatronic system. And for second order system, the time spec, okay, the time spec is shown here, okay, where the overshoot, the peak time, and the settling time, okay, is shown here, and the rise time as well. So rise time is similar, like first order, which is T90 minus T10%. And the peak time is usually at the peak of the response. So we call it as the peak time. And settling time is over here, which is plus minus 2% of the final value. So if the final value is equal to 1, so plus minus 2% can be 0.98 and 1.02. Which one comes first? Okay, either 0.98 or 1.02. Which one comes first? That is the measurement of the settling time. And for peak time, usually we are using a formula. Okay, if you're second order system, so you can remember this formula. Peak time is equal to pi divided by omega d. Pi is 3.14. And omega d is omega n 1 minus zeta square. This is the formula for omega d. And for overshoot percentage, shown here, is minus e minus pi zeta over 1 minus zeta square. And all of this is multiplied by 100%. Okay, and settling time is 4 divided by 4 zeta omega n. Okay, so usually we can say that it is modulus of real part. Okay, so real usually represent the x-axis of S-plane. Okay, like this. And for the omega d, okay, omega d is pi divided by omega d. So usually is EP pi divided by imaginary. Okay, so in this case, pi divided by omega d, or pi divided by omega n 1 minus theta square. Okay, magnitude of the value. If the value is negative, so we make it magnitude modulus, so it become positive. So we get the time value. Okay, understand? Understand or not? Like this. Okay, zeta. Okay, so this part is usually is negative zeta omega n, and this part is usually omega d, which is equal to omega n 1 minus zeta square. So this one is, we call it as the real part, and this one we call it as the imaginary part. Okay.
Excuse me, doctor.
Yep.
I have a question. Which is considered the most preferred response out of them?
Okay, the most preferred response, as I told you before here, okay, if you want to design any system, robot system or motor system or whatever system you want to design, okay, so the best zeta according to the book is this one, okay, under them. So under them is the damping ratio is between 0 and 1, okay. So the best response, it can give you the best response, it goes up and it goes down like that, okay. So we don't want like this one, not a good response. This one is the best response. This one over them quite slow. You can see that critical dam also slow, okay. So we don't want respond like that. So try to design if the input is square and the response should be the blue one, okay. It follows and goes up and then go down, like that. This is the best response. And to get this, you must set your zeta is between 0 and 1, or the best one is 0.704 from my experience. Did I answer your question?
Yes, doctor. Thank you.
Okay. So the formula would derive based on the purely second order system. Therefore, the formula valid only for second order system without zero. Okay, without zero meaning that it is G omega n S square plus okay. So this is K. So if you have zero, this is without zero. Okay. So if you have zero, you have something like this. So this is what I call a zero. Okay. However, under certain conditions, a system with more than 2 poles can be approximated to second order system. Okay, let's say this is the second order, then in the design, usually they have another one, the third pole, okay, maybe S plus 3, S plus 4. So in this case, the complex poles that dominate the overall performance are known as dominant pole. So this one is considered as dominant pole, and this one is considered as third pole. Why we call it dominant poles? Because this poles is very near to the imaginary axis. And when the poles are near to the imaginary axis, it has a great influence towards the output response. I give you 3 cases, okay? Where case 1 is the pure third order. Case 2 is a second order approximate. And this one is pure second order. Okay, so approximation is valid if the third pole, the ratio of the third pole towards the real are more than 5 times. Okay, it's more than 5 times. P1 and P2 are the dominant poles. You must understand this word. Okay, so if the let's say we have a -1 plus minus J2, this is dominant pole. Okay, so third pole, let's say we have a third pole equal to let's say -10. So the ratio is -10 divided by -1 is 10, which is greater than 5. So when it's greater than 5, meaning that the system is third order, but can be applied as a second order approximation, valid. Okay, it's valid because it's greater than 5. But if you have a third pole is equal to -2, okay, so the ratio now is -2, the value of the third pole modulus divided by the real part, which is real part of the dominant pole, so it's equal to 2, which is less than 5. So when it's less than 5, the system is third order and not valid for second order approximations. Okay, so the border is 5. Okay, the rule of thumb is 5. Do you understand what I say? So in this case, this one is a purely third order. This one is second order approximation, even though it is third order, because the third order is far, far away from the imaginary axis. And this one definitely is a second order because there is no third pole. Atika, faham tak apa Prof cakap?
Faham tu.
So the zeros affect the amplitude of response, but do not affect the nature of the response. See? So this is the factor of zero. Okay, affect the amplitude of response, amplitude, but do not affect the nature of the response. Consider a second order system with pole here. This is the pole, and we add 0 at -3, -5, and -10. Okay, so the closer the 0 to the dominant pole, the greater the effect of the transient response. Of course, -3 will play a great function and more and dominant because it near to the dominant poles. Okay, so you can see here when 0 at -3, okay, the amplitude is high. Okay, -5 and -10, and then no 0. Okay, it is faster, but it gives you a bigger amplitude. Okay, and overshoots. So by adding a 0, so when you take a time response, I always, please take note, this one is very important. If you want to find a time response, must based on closed loop. Closed loop transfer function. So when you have a closed loop transfer function, CL transfer function, so you can inject the step and then you find the response as shown here. But this one, due to the zeros, okay, due to the zeros, you can see that the response go down a little bit, and then it goes up after that, and will give the expecting time response of the second order system. So this one we call it as a non-minimum phase case. Okay, non-minimum phase case. So as I told you before in design, okay, what is our goal? First is we want a stable system. And then we want a faster response. And the last one is we want a zero steady state error. Okay, so we have 3 basic main objective. So what is a steady state error? Steady state error is the difference between the input and output prescribed by the test input as t towards infinity. We have input here, which is 1.0 volt. And then we have output 1, which is the final value is equal to 1. And this one, final value is equal to 0.6. Let's say this one is 0.6. This one is 1.0. Of course, for output 1, ESS, output 1, the steady state error is 1 minus 1, so equal to 0. But for the output 2, okay, the steady state error is 1 minus 0.6, so 0.4. So this is not good. Okay, this is not good for our system design. So we must make it 0. Okay, by using a controller. And in order to do that, we can use the calculation approach, which is using a final value theorem, which is ESS equal to limit t towards infinity, E of t, which is equal to limit s to 0, SES. Okay, where error is the difference between the input and output. R is input, C is output. And ESS is depends on the input and system type. So we have a type 0, type 1, and type 2. Okay. This will give you the static error constants value, which is the position error constant, velocity error constant, and acceleration error constant, which is KA. And the formula for the steady state error is shown here. E when t towards infinity, limit s to 0, SRS 1 plus GS. Lokman cek lah.
Ya, saya.
What do you understand by type 0, type 1, and type 2?
Can you repeat the question, sir?
What do you understand by system type 0, type 1, and type 2? Lamanya jawab. Nak tunggu.
Sekejap.
Tak
Type
tahu.
yang mana, sir?
Banyak ya?
Case, yang case punya ke yang
Ni ha.
yang untem tu, tuan?
Ni. Slide 20. What do you understand by type 0, type 1, type 2? System type. General lah, general question. Tak tahu. Si Micin.
Hi, Doctor.
Hai.
I
What do you?
also don't know, but
You also don't
maybe
know.
like rand input.
You also don't know. As well, this example, okay? S0. So this is an example of type 0. Okay. Type 0. Okay. There is no poles at the origin. Okay. Type 0. Okay. And then another example, which is 1 over okay. So this one we have S over here, minus 3. n minus 4. This one we call it as a type 1 because 1 pole at the origin. And the third type is this one, 1 over, okay, so minus 5, minus 6, and we have a at 0. So this one is type 2 because 2 poles at the origin. Understand? Chua, do you understand?
Yes, doctor.
Understand?
Yeah.
Liana, Camelia?
Yes, doctor.
Lama tak jumpa? Kalau tak datang kelas, beritahu message phone ada kan? Faham tak apa saya cakap ni? Type 0,
Faham.
type 1, type 2. Faham
Faham.
Okay, alright. Lama tak jumpa. Right. So design with gain adjustment. If there is no question, we proceed. Design with gain adjustment, second order approximation. The formula for the time response specification only valid for a pure second order system without zero. Conditions for second order approximation, okay, that must be fulfilled. High order poles are 5 times further into the left that the dominant second order poles, as I described just now kan, yang less than 5, sorry, greater than 5 and less than 5. Okay. Closed loop poles are nearly cancelled by the close proximity of higher order poles. Okay, closed loop zeros must be cancelled out by the close proximity of the higher order poles. Misal kata this. Okay, you have a sorry. Like this, -2. So this one, another zeros, which is over here, which is -2.1. So the zeros minus 2.1 and poles -2 can be cancelled out each other. Okay, so dia kosong-kosong balik lah. It's 0, 0. Okay, because the location of the poles -2.1 and zeros -2 are very near each other and nearly overlap. So we can say that it can be cancelled each other. So this is the how to explain the approximations. So we have open loop poles as here, closed loop poles as blue, and closed loop zero as circle. Okay, so open loop is black, closed loop is blue color. So the closed loop pole actually is the root locus lah. So you can see that the location of P3, okay, here, right, and here, and here when we add 0. So you can see that when we add 0 over here, so the root locus is not crossing the imaginary axis. So it goes towards infinity and infinity. Similar to this one as well. Okay. When the locations of the third poles is near to the 0. So more or less, there is no critical gain because it didn't cross the imaginary axis. So higher order pole cancels the closed loop zeros. So for gain adjustment, design procedure is first you sketch the root locus, assume the system is a second order system without zero, and find the gain to meet the specifications, and justify the second order approximation by finding higher order poles. Okay, So please remember the procedure, example 1. Okay. Con Yawen,
Yes, doctor.
can you read the examples, please? I puasa mah.
Given a unity feedback system that has the forward path transfer function, A. Sketch the root locus. B. Design the value of K to yield 10% overshoot. C. Estimate the settling time, peak time, rise time, and steady state error for the peak of K in B. D. Determine the validity of your second order approximation. And E. Double check your result using MATLAB.
Okay, sketch the root locus. So in this case, root locus is given. Okay, so we're going to sketch, right? Using MATLAB. So I share you the screen. Okay, can you see my MATLAB, guys?
Yes.
Yes.
So we assume K equal to 1. G 1 over S cubic plus S square plus plus 48. Okay. This is we call it as the open loop. Okay. Sorry, a root locus. Okay, root locus is based on open loop. Then if we want to see the time response, we have to write a program so that G will become closed loop. So G is the open loop transfer function. So I assign T as the closed loop. Okay. Okay, guys. T is the closed loop. So T is equal to G divided by 1 plus G. So this is the feedback formula. Okay, is the feedback formula. Okay, like that, right? And then to see the root locus R locus G. Roman, off mic. Off mic. Somebody off mic, please. Bising. Thank you. Okay. R locus G. So we enter. And then we put the grid. Okay. Can you see? Can you see the root
Yes.
locus? Okay. So that is the root locus. So you assume that this one is given. Okay. Okay. Okay, so copy figure. One B. Okay, so that is your two. And then in order to find the time response, so we go back to the MATLAB program. Okay, here. So we write a step, okay? Step, one verb, T, okay? Then put the grid. Okay, so and this is the closed loop response, okay, before gain adjustment. Before gain adjustment. Okay. So you want to see what is the settling time. Okay, so that is the settling time. Okay. Right. Right. So now we go back to the slides. Okay. So the red color is the answer. Okay. You can ignore it. Right. So first we sketch the root locus. Okay, I already teach you how to do the programming. Okay, so Haris Haikal,
Yeah.
how many root locus path in this plot?
3.
Why?
Because it has 3 color.
Because it have a 3 open loopholes. Yeah. Okay.
Yeah.
3 colors pula. Tak betul jawapan tu. Okay. So what is this, Haris Haikal?
Breakaway point.
Breakaway point. What is this? RL intersection with J omega. Okay.
Okay.
Where K critical occurred. Okay. So the time response is here, guys. Okay, is the closed loop time response. K is equal to 1. Guys, take note. Settling time is 2.42 seconds, as I showed you before. And final value is 0.0204, which steady state error is 0.98. Wow, that is too big, right? So we have to improve it from 0.98, reduced it for somehow by using a P controller, right? So as I told you, the question, this is given, the spec design, okay, given spec design, given, which is a 10% overshoot. So 10% overshoot can be converted into zeta value by 3 ways. The first one is using a formula. Okay, exponent pi zeta over 1 minus zeta square multiplied by 100. The second one is straight away using this formula. Okay, and then the third one is by using a graph. So which one is the best, Prof? The best one in 5 seconds is this one, using your graph. Provided you have a ruler, okay, and then it goes down. So you get the 10% here. And this here is 0.591, okay? 5-second method. Use the third graph, okay? So it's attached in the test and in the exams. Right, and then for zeta 0.59, zeta 0.591 can give us, okay, an angle, okay, an angle which is inverse cos 0.591, 53.77 degrees, okay? So you just, take a ruler, and then print out first, take a ruler, and then use your protector. This is the theta, and this is the dominant pole under consideration, which is minus 2.03 plus minus 2.77 at gain K 45 and 6. Okay. And then you can calculate the gain K over here by using L1, L2, and L3. Or if you don't like theorem Pythagoras, you just take this value, the intersection value, and you insert inside the angle, the gain criteria, which is S plus 2 over S plus 4, S plus 6. Okay, do you understand? Like this. K is equal to S plus 2, S plus 4, S plus 6. Okay. Then the value is minus 2.03. Okay. So replace S with minus 2.03 plus J 2.77. 2.77. Okay, so what is this symbol? Guys, what is that symbol? Liana, Camelia. Symbol apa itu?
Absolute ke doktor?
Huh?
Absolute ke? Absolute.
Magnitude.
Oh, magnitude. Okay.
2.77 plus 4. And then minus 2.03 plus J 2.77 plus 6. Okay. Magnitude, guys. Tanya lah. Asnawi. Example. Minus 2 plus J3. Asnawi?
Ya doktor.
How you
Yeah.
get this magnitude? Contoh. Itu je lah aku tahu. Astaghfirullahalazim. Istighfar banyak-banyak 9 tambah 4 berapa? 13.
13.
So this is how you calculate after you simplify this one. Okay, so we have two ways. One is using L1, L2, L3. You calculate using the theorem Pythagoras. Or if you don't like theorem Pythagoras, you want to see the graph, you don't have printer and so many excuses, you use this method. Okay, and then you get K equal to 46. Jelas guys? Clear guys? Clear?
Yeah.
Clear. Right, so this one is second method. Okay, so as I mentioned you before, minus zeta omega n plus j omega d, this one is the real part, this one is the imaginary part. So the dominant pole here have real part and imaginary part. So you just take the value, the real part goes to settling time, 4 divided by real, 4 divided by 2, so you get 1.97 seconds. And this one, the imaginary part, it goes to the peak time, pi divided by imaginary, pi divided by 2.77, 1.13 seconds. And zeta omega n, which is equal to 2.03, we know zeta, but we don't know omega n. So omega n 2.03 divided by 0.591, 3.43 radian per second. And omega NTR is equal to 1.8346 because because it's located in the standard normalized rise time. So rise time is equal to 0.53 seconds respectively. Or simply you can use this graph, standard graph, okay, which is 0.591 is somewhere here. Okay, guys, and it goes here. Yuki Wong. Yuki Wong,
Yes, Doctor.
what is the equation for this line? This line.
Not sure, Doctor.
Not sure.
Yeah.
Chong Joan, never mind, it's okay. Chong Joan,
Yes, Doctor.
what is the equation for this line, ma? Tak tahu. No, no idea. Okay, Chong Hoi Ki. Miss Chong, what is the equation for this line? Chong tidur ah? Oh, dia puasa, dia tidur ah. Patrick, what is the equation for this line?
Y equal to 1.76x cubed minus 0.417x squared plus 1.039x5.
Wah, pandai ah. Inilah, ini punya equation lah. Semua tak tahu, tidur semua. Omega NTR is equal to 1.76 zeta cubic minus 0.417 zeta square plus 1.039 zeta plus 1. Okay. Okay, guys, don't sleep. So steady state error. So the system is type 0. Why? There is no S in front of S plus 2. Okay. So this is 1. Kan? So this is a type 0. So if type 0, dia adalah KP lah. Okay. Position error constant. So we use this open loop transfer function. Okay, this is a formula for error, steady state error, but we have to find the KP. So KP is the position error constant due to the type 0, kan? So K over S plus 2, S plus 4, S plus 6. So insert the K that under dominant pole just now, which is 46. So 46 divided by 48, 0.96. Enter to the formula back again. 1 over 1 plus 0.96, so 0.51. Previously, all 0.98. The new one, after gain adjustment, is 0.51. Meaning what? It's reduced by 50%. Okay. So determine the validity of the second order. So at here, the dominant pole is here. Okay, and the gain is 46. So the third pole is minus 7.95. How do I get this? Okay, the way to get it is you find the characteristic equations. Okay, this is the characteristic equation. S cubic 12s squared plus 40s plus 48 plus k. But k is 46, ma. 48 plus 46 is 94. Okay, so you use your calculator. Okay, you use your calculator. Okay, and find these roots. Okay, these roots. Okay, so you find this root, then you get minus 7.95 minus 2 plus minus J 2.77, which is here. Okay, that's why I get minus 7.95. Okay, then the ratio is 7.95 divided by 2.03 equal to 3.9 less than 5. So second order approximation is not valid due to the ratio is less than 5. The system is original third order system. So we insert k equal to 46 to the system. Now you can see that the settling time is 1.86. The final value is 0.487. Error is 0.513. And if we compare gain adjustment before and after, okay, so this is the comparison. Okay, so observations faster transient by 23%. Okay, this is the settling time at 2 point something, but now the settling time is 1.29. So the response become faster, 23%. Steady state error reduced by 50% from 0.98 to 0.513. And then the overshoot is 8.85%. There is a little bit overshoot over here. Okay, after we apply gain adjustment. Any question, guys? Ada soalan? Any question? Any question? Want to ask?
No, Doctor.
All right, brothers, any questions? Safwana, ada soalan? Any question? Safwana, datang? Tak datang.
Tak sihat, Doktor.
Oh, tak sihat. Okay, syabab. So during iftar, be careful when you buy food for iftar, make sure it's clean. Okay, I'm worried about food poisoning, so just be careful. Ivan, any question?
No question, Doctor.
Okay, if no question, it's 1 o'clock already. So I see you next week, guys. Okay, take care.
Thank you, Doctor.
Okay, bye bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Doctor.